Section 1.7, linear independency, which is the same as section 4.3 in Edwards' textbook. What's the definition of linear combination? If there exist constants C1, C2, all the way to Ck, and we are able to express a vector as sum of the scalar multiple of individual vectors like v1 through vk, this format is called linear combination of what? v1 through vk. In other words, somehow we will manage to get a hold of constants such that when we multiply the first constant by the first vector, second constant by the second, and so on and so forth, and add up the results, then we can say the vector v has been expressed as a linear combination of three vectors, let's say the vectors v1 through vk. Case in point, let's say you got what? These three vectors, let's say v1 through v3. The question is, express this vector 13, 8, 13 as a linear combination of v1, v2, v3. So what that means, and sorry, v4 as well, 4 vectors. So what that means is what? We're supposed to express v as a linear combination of these 4 vectors, meaning we're supposed to find constants C1 through C4 such that v can be written as C1 v1 plus C2 v2 plus C3 v3 plus C4 v4. Question is, when we say there exist, that means we must find those constants. Turns out 0 of these minus 3 of v2 plus 5 of v3 and plus 1 of v4 gives you your desired vector. In this case, to get 13, 18, 13, we multiply this guy v1 by 0, v2 by negative 3, and v3 by 5, and v4 by 1. So C1 has to be what? 0. C2 has to be negative 3. C3 has to be 5. And C4 has to be 1 for what? Vector v to be expressed as a linear combination of the remaining 4 vectors. So that brings us to a definition of spanning set of vectors. If every vector, notice the catchword is every vector in a vector space, let's say you are in 3-dimensional space, so vector space would be like R3, can be written as linear combination of v1 through vk. We say that v is spanned or generated by vectors v1 through vk. And we call these set of vectors as a spanning set for the given vector space. Or we say what? These guys span the vector space. In other words, if every vector can be expressed in terms of what you claim as to be the spanning set of a vector space. So we say those set of vectors span what? The vector space V3. Case in point would be something like, let's say, I would say that what? I, J, and k vector, remember those were the special unit vectors in positive x and y and z direction respectively, spans, let's say what, R3. Why would I say that? Well, because what? If you give me a random vector in R3, let's say v, which is like, let's say x, y, z, okay, some random vector in R3, so the vector space is what? R3. So the claim is these 3 vectors span R3. So what does that mean? That means any random vector you select in R3, you can write it as what? C1i, C2J and plus C3K. Well, you guessed it. So this has to be what? The same as what? Let me just write it up here. X comma Y comma Z can be written as what? X times I, is that right? Plus Y times J plus what? Z times K. So remember, in this case, C1 is X, C2 is Y, C3 is Z. Specific case, suppose I have, let's say, 2, -3, 1 vector in what? In R3. So the idea is ijk spans any vector in, the vectors in R3. So what does that mean? That means I can rewrite 2, -3, 1 as 2 times I plus, or I should say minus 3 times J plus 1 times K. Do you see it? So in this case, C1 is 2, C2 is -3, and C3 is 1. But keep in mind, spanning set is not unique. So it just so happens that IJK, later on we will learn, those are called standard bases for R3. In other words, I can still come up with different set of vectors in R3, which any other vector in R3 can be written as a linear combination of those. So IJK are not the only spanning set for R3. When you have a system of linear equation, let's see, you got 3 equations, 3 unknowns. This is how we write this system in compact form. So the system 1 has a solution if B, that means what? The column vector is linear combination of columns of, coefficient matrix. In other words, there goes your first application of why we care about linear combination. Notice the matrix of coefficients happens to be this matrix, which is what? 3 by 4. This is the matrix, column vector of matrix of unknown, which is 4 by 1. And this is the matrix of the constant, which is also 4 by 1. Question, when do we say this system has a what? Solution? Answer, if you can write B as a linear combination of columns of what? Of A. What does that mean? That means if I can write what? B, which is what? 13, 8, 13 as linear combination of columns. So that would be 1, 2, 3. C2 is what? 2, -1, -2. And C3 is what? 3, 1, 1. And C4 times 4, what? 0, 2, correct? But that's exactly what we did a while back. So we decided to call this now the what? Column vectors of constant, and those are columns of matrix what? A. We decided, oh my goodness, if C1 is 0, C2 is -3, C3 is 5, C4 is what? 1. You can write what? B as a linear combination of columns of matrix A, which happens to be matrix of coefficients. Speaking of columns of A, we have column space of A, which that means all linear combinations of columns of A, row space of A, which means all or linear combinations of rows of A is called row space. So this guy is called column space, correct? Column space of A. And this guy is called row space of A, which is column space is all linear combinations of columns of A. That means the spanning set. And row space is all linear combinations of rows of A. In other words, sometimes the question might be, given 2 vectors, okay, can you determine if these two vectors, if what? This vector, okay, if this, can you tell us, is this vector in the spanning set of U1, U2? Okay, so given these two vectors, U1 and U2, can you determine, can you prove that this vector is in the spanning set of what? U1 and U2. Excuse me. Well, what does that mean? In other words, all that means is, can we write vector V as a linear combination of U1, V2? In other words, can I write V, which is what? 1, negative 1, negative 1, as linear combination of U1, U2, which is what? C1 times negative 3, 1, negative 1, C2 times 5, negative 2, 1. Remember, when we say can we, or there exists C1, C2, that means we literally have to find C1, C2, correct? So it turns out when you kind of form augmented matrix, you know, a hashtag kind of a deal, you know, form a system of linear equation, put it in row echelon form, well, you got what? Two unknowns, right? Two unknowns, but three equations, all right? You know what the equations are, don't you? That would be like negative 3c1 plus 5c2 is equal to 1. C1 minus C2 is equal to negative 1. And negative C1 plus what? C2 is equal to negative 1. Notice I got three equations, but what? But two unknowns. So that's what this is. And remember from previous sections, we learned if you have more equations than unknowns, there are two possible solutions. Either you have a unique solution or you don't. There is no other possibility. So if you put it in row echelon form, even though the last row is 0, which is okay, but the first two rows have what? Pivot elements or leading ones in the appropriate columns. So it turns out you do have a what? Unique solution. And in this particular case, what? Incidentally, this should read, my apologies, this should read what? Oh, C1, C2, because that's what we're trying to solve for, correct? So this should read C1, this should read C2, so C1, C2, believe it or not, comes up to 3, 2, so that means what? We have a unique solution. Therefore, the answer is yes, V is in the spanning set of U1, U2. So here's the final answer. Yes, V is in what? The what? The spanning set of U1, U2. In other words, I can write V as a linear combination of U1 and U2. All right. So one more question. Can you show that V1, V2 spans R2? In other words, no matter what you select in what? On X and Y axis, can you write it as linear combination of these two vectors? Remember, in two dimension, the standard to what? Basis, that's what we're going to learn later, is I and J. But turns out those are not the only two vectors which I can write any other vector in R2 as a linear combination of it. So it turns out these guys will do the job just as well as I and J. Check this out. So the solution starts from here, right? So what we say is what? Let x, y, so be in R2. In other words, let's call this O vector V, any random vector in R2. And C1, C2 be real numbers. Question is, can I express this vector, let's call it O x1, y1, let's call this x1, y1, or even better, let's call it x1, x2, just to be consistent with the rest of the solution. So let vector x1, x2 to be in R2. So this means an element of. So an element of. Can I write x1, x2, which is a random vector in R2, as a linear combination of what? v1 and v2, which are given to me. When you say, can you write it? The question is, can you find C1, C2? Okay, if you can get your hands on C1, C2, then you can say, yes, these guys span R2. If you cannot, then the answer is no. In other words, it all depends on what? System of linear equation which you kind of come up with. In this particular case, when you multiply C1 by 1, -5, C2 by 6, 3, set it equal to x1, x2, you got a vector on the left side, vector on the right side. So the only way these two vectors will be equal if C1 plus 6C2 is equal to x1 and -5C1 plus 3C2 is equal to x2. I know we don't have the numbers on the right side, but that sometimes happens because you cannot choose any specific numbers. So the proof has to be in generality. Do you see it in general case? So the idea is what? Can you solve for C1 and C2? Turns out if you put this in row echelon form, augmented matrix that is, you get 1, -5, 6, 3, line x1, x2. And if you put this in row echelon form, lo and behold, you will find out what? C1 and C2, you have a unique solution. And this is how the solutions look like. Therefore, these two vectors, we say they span R2. In other words, the entire conclusion depends upon what? Whether the system of linear equation is consistent or not. If the system has a solution, then these guys do the job, which is span R2, which means any other vector in R2 can be written as linear combination of V1, V2, regardless of what you select in R2. If it is not consistent, the system that is, then you can say, no, they don't do the job and they don't span. Incidentally, the vectors in the spanning set for a what? Of a vector space, those are like the building blocks. In other words, any other what vector can be built based on these two vectors if your answer is yes, which in this case it is. So specifically, let me just give you a specific case. Remember now, we are finished with this problem, correct? Specific case might be like you might choose vectors, let's say 5, I don't know, 0. So in other words, let's say this is your x1, let's say this is your x2. So C1 is what? 5 minus 0 over 11, which is 5 over 11. C2 is what? 25 plus 0 over 33, which is 25 over 33. So what are you saying? I'm saying 5, 0 can be written as a linear combination 5 over 11 of 1, -5, and what? 25 over 33, what? 6, comma 3. But remember, this can be done for any vector in R3, not just 5, 0, any vector. Therefore, the answer is what? Spanning set. So these guys span what? R2. In general, if you have two non-collinear vectors in R2, they span R2, and they cannot be 0, all right? They have to be non-zero vectors. Any three non-coplanar vectors in R3 span R3. Non-collinear means they are not parallel. They don't lie in the same straight line. Non-coplanar, that means they don't lie on the same plane. Coplanar means same plane. So in this particular case, the question is, do these guys span R3? Well, you have to form a what? Select just like this, a vector in R3, okay, call it x1, x2, x3, and form this what? System, form this linear combination. Of course, then you will have x1, x2, x3, c1, v1 plus c2, v2 plus c3, v3, which will give you three equations, three unknowns. Then you have to decide whether that system is consistent or not. So we can answer the question and say, yes, they span, or no, they don't span. Turns out in the next section, when we learn about determinant of a matrix, there is a fast way to determine if a system is consistent or not. So it turns out if the determinant of the what given vectors is what? 0, then they are coplanar, right? So therefore, what? They do not span. However, for our case, you know, these three vectors, the determinant comes up non-zero, so they are non-coplanar. Therefore, yes, they do span R3. Do you see it? So that's pretty much in a nutshell what that guy is. But in case you were wondering how the setup looks like, as I said, let V to be equal to what? Vector in R3. Form this equation, okay? Then you would have this system of equation, 1, 2, 3 equations, 3 unknowns. My job is not necessarily solve this system. My job is what? To see, check and see if the system is consistent or not. Consistent or not, meaning does it have a solution or not? But let's say right now my hands are tied, so I don't have, better ways, efficient way of knowing that. So for meanwhile, I have to do it the old-fashioned way. And lo and behold, check this out. Turns out what? You have leading ones in every column. So that indicates you have a unique solution. Do you see it? Because you have a solution, then you can come back here and say, yes, they do span what? R3. What does that mean once again? Any vector in R3 can be written as linear combination of the three vectors which you gave me. The next question is, what about we have polynomials? In other words, what if we got these two polynomials? The question is determine whether or not this third polynomial lies in the spanning set of these two. So what does that mean? So the solution is as follows. So if P is, this is an element of, so that's the notation for member of a spanning set. So this notation backwards E means there exists. You know what there exists is, don't you? That means we must find them. There exists A and B real numbers such that, so ST stands for such that, what? A P1 plus B P2 has to be the same as the polynomial, which we're trying to see if it lies in the spanning set of these two polynomials. So what do? You write the polynomial, which you're trying to find out if it lies in the spanning of P1, P2. So you kind of go 2x squared minus x plus 2 plus a. Remember, we used to call this C1, we used to call this C2. Some books, you know, instead of a C1, C2, they might use AB. I just want to bring this to your attention. So there it is. So now, if you kind of manipulate this right side and kind of factor out what all the x's, the constants, and the x squared, Now you got a polynomial on the left side and a polynomial on the right side. The only way these two polynomials will be equal if the corresponding what? Coefficients match. Do you see it? Okay, including the constants. So what that means, I have to set 2 is equal to b, -1 equal to a minus b, and 2 is equal to 3a minus 4a. It looks like I have more equations than unknowns, so either you have a solution or you don't. If you have a solution, then we say, aha, that guy lies in the spanning set of P1, P2. If you don't have a solution, then it doesn't. So it turns out here, A is equal to 1, B is equal to 2. Therefore, we say yes, yes, yes what? P is an element of the spanning set. So of all the polynomials, second order degree polynomials, which you can write as a linear combination of these two, this guy happens to be one of them. So there are 10 million other ones, but this is one of them. In general, any second degree polynomial can be written as linear combination of these. Thus, what? These guys span what? P2. P2, so we say P1 and P2 span capital P2. Capital P2 means all set of polynomials of what? Of degree 2 or less. So any polynomial of degree or 2 less, you can what? Write it as linear combination of these two what? Polynomials. And that will take care of spanning set and linear combination. In the next video, we'll talk about linear dependency and independency. Thank you.